Hello GATE aspirants, welcome to part 6 of GATE Electromagnetic Theory series. Question number 28. A point charge is placed between two semi-infinite conducting plates which are inclined at an angle of 30 degrees with respect to each other. The number of image charges is. Here first calculate n is equal to 360 upon theta. So that is 360 upon 30 which is equal to 12, and this is even number. So number of charges will be minus 1, so n minus 1, so this will be 12 minus 1, that is 11. So answer is 11. Answer in the answer key is also 11 to 11. Next question. A beam of X-ray of intensity I0 is incident normally on a plane sheet of thickness 2 mm. The intensity of the transmitted beam is 0.025 I0. The linear absorption coefficient of the metal sheet is. Now I is equal to I0 e raised to minus lambda d. I is equal to I0 e raised to minus lambda d. This is given, so I0 will cancel. So this is 25 upon 1000 which is equal to e raised to minus lambda, and this distance is given, thickness is given, that is 2 mm. So we can take reciprocal on both sides. 25, 1000 upon 25 is 40, that is equal to e raised to lambda into 2 mm. That means ln of 40 is equal to lambda into 2 mm. So lambda is equal to ln of 40 upon 2 into 10 to the power minus 3, and this is equal to 1844.4. So this will be the answer, and answer given in the answer key is 1844.4 to 1844.5. Question number 32. The space between two plates of a capacitor carrying charges plus Q and minus Q is filled with two different dielectric materials as shown in the figure. Across the interface of the two dielectric materials, which one of the following statements is correct? So this is given, and there will be, here we can consider that there are no free charges. So there are no free charges here. If that is the case, then d bar we can write, see, parallel component is always parallel component is always, or the tangential component is always continuous. So we have to consider perpendicular components. Now d1 minus d2 perpendicular, that is equal to the density, but there are no free charges here, so this will be 0. So we can say that d bar is continuous. And according to boundary condition, this d bar parallel and e bar parallel, they are also continuous. So parallel component or tangential component of electric field is continuous, but we can't say that for sure for perpendicular component. So here d bar is continuous and e bar is discontinuous. So option C is correct. Next question. A charge minus Q is distributed uniformly over a sphere with a positive charge Q as at its center in 1, also in 2. A charge minus Q is distributed uniformly over an ellipsoid with a positive charge Q at its center. With respect to the origin of the coordinate system, which one of the following statements is correct? Now in each case we can calculate monopole moment. So monopole moment is equal to summation over charges. So in each case we have two charges, minus Q and plus Q. So this will be 0. So monopole moment is 0. Now we can calculate dipole moment. Now dipole moment is summation over I, Qi, Di. But here it is symmetric distribution, here it is spherical distribution, but it is symmetric about origin, and this is ellipsoid which is also symmetric about origin. So this will also be 0 because this charge is minus Q and plus Q, so this will also be 0. So dipole moment is also 0. So option A is correct. Dipole moment is 0 in both 1 and 2. Next question. A long solenoid is embedded in a conducting medium and is insulated from the medium. If the current through the solenoid is increased at a constant rate, the induced current in the medium as a function of radial distance r from the axis of solenoid is proportional to. Now we know line integral of E dot dl is equal to minus of dou b by dou t over area. Now we will calculate this for two regions. So consider for r less than r, where r is radius of that solenoid. So this will be E into integral over dl. So that will be 2 pi r. So into 2 pi r, this will be equal to minus of. Now we know for solenoid B we have to calculate. So B is equal to what? B is equal to mu naught into n into I. So dou B by dou T, that will be equal to mu naught Ni into di by dt. So this is the case. Now we have to solve this. So this will be mu naught into n into di by dt into this area. Area integral is pi r square. So this will be pi r square. So this is for r less than r. Now we have to calculate for r greater than capital R. Left hand side will be same, E into 2 pi r. This will be equal to, here minus sign will also be there, and this will be equal to mu naught into Ni into di by dt. Now we know that inside, this will be inside the solenoid, and B is equal to 0 outside of it. So this integral that we are taking, this surface integral, it will be from, so this is radius of r, this is the case, and we are considering loop like this whose radius is r. Then this dA, this integral, we have to consider till this point only, because outside of that B will be 0. So this will be minus of, and this area will be simply pi r square, because this limit will be till capital R only. So that area only we have to consider. So now for first case, this will be E, and then we have to find out dependence of R. So this R and R square, so it will be proportional to R. And for this case, E is proportional to, this capital R square is constant, so it will be proportional to 1 upon R. So here option D is correct. R inside the solenoid and 1 by R outside the solenoid. Next question. A plane wave after passing through an optical element emerges as this x cap minus I y cap, where k and omega are the wave vector and the angular frequency respectively. The optical element is. Now here this initial state is given, and it is x cap plus I y cap. That means it is having both these components, that means it is circularly polarized, and this is plus sign, so that means it is left circularly polarized. And the final state or the emergent state is x cap minus of I y cap. So here x cap component is same, but this is reversed. So this is right circularly polarized. Now this is plus 1 to minus 1. So this is phase difference of, or phase change of pi. And phase change of pi means corresponding path difference of lambda by 2. So this is path difference of lambda by 2. So that means it is half wave plate. So option B is correct. Next question. A monochromatic plane wave wavelength lambda is equal to 600 nanometer, E naught exponential I kz minus omega t is incident normally on the diffraction grating, giving rise to a plane wave E1 exponential I k1 bar dot r bar minus omega t in the first order of diffraction, n is 1. Here E1 is less than E2, E1 is less than E0, and k1 bar is equal to k1. K1 bar is given, it is k1, magnitude of k1 into 1 by 2 x cap plus root 3 by 2 z cap. The period of the diffraction getting is, so this is given, and initial wave is it is in k direction. So k bar is equal to magnitude of k into we have z cap. So these are our two vectors, k1 bar and k bar. So from here we can see, if this we are considering direction of z, then if this is k bar, then this is in the, and this is x, then this will be direction of k1 bar. So this will be angle theta between them. So we can calculate this theta. So sin theta will be k bar cross k1 bar upon magnitude of k bar and k1 bar. So this will be equal to, sin theta is equal to, k bar is this, k bar into z cap. So this k bar will cancel out, cross with k1 bar. So this k bar will cancel out, and we have cross into half into x cap plus root 3 by 2 z cap. So this will be half into z cap cross x cap. So that will be equal to z cap cross x cap, that will be equal to z cap, y cap here, and this will be z cap cross z cap, so that will be 1 only. So if we consider magnitude only, so then sin theta will be half. So if sin theta is half, and we have d sin theta is equal to n lambda, so that means d into sin theta is 1 by 2, n is 1 and lambda is 600 nanometer. So d is equal to 1200 nanometer, that is equal to 1.2 micrometer. So answer will be 1.2. So these were all the questions from GATE 2015 paper. If you like this video, please give it a thumbs up and subscribe to my channel for more videos. Keep learning.